Hello everyone, so our group tasked to do a reporting about evaporation. So what is evaporation? Evaporation is a process by which an element or a compound transitions from its liquid state to its gaseous state. Below the temperature at which it boils, in particular, the process by which liquid water enters the atmosphere as water vapor. Evaporation also happens when liquids change into gas. It is also a part of a water cycle. One common example of evaporation is the steam rising from the head of cup of a coffee. This heat rising out of the cup helps the coffee to cool down.
What is evaporation? Evaporation is a type of vaporization that occurs on the surface of the liquid as it changes into gas phase. When water is heated, it evaporates. The surrounding gas must not be saturated with the evaporating substances. The molecules move and vibrate so quickly that they escape into the atmosphere as molecules of water vapor. When the molecules of the liquid collide, they transfer energy to each other based on how they collide with each other. When a molecule near the surface absorbs enough energy to overcome the vapor pressure, it will escape and enter the surrounding air as gas. When evaporation occurs, the energy removed from the vaporized liquid will reduce the temperature of the liquid, resulting in evaporative cooling. Examples of evaporation that powers the evaporation process is heat from the sun and the solar energy.
What are the factors that affects evaporation? There are four factors which affect the rate of evaporation: the surface area, the temperature, the humidity, and the wind speed. So what is surface area? Surface area. We know that evaporation is a surface phenomenon. If the surface area is increased, the rate of evaporation increases. For example, while putting clothes for drying up, we spread them out. We spread the particles. Next is the temperature. With the increase of temperature, more number of particles get enough kinetic energy to go into the vapor state. Just like here in the Philippines. Grabe gid sang init. Pero sa dagat na kadasig mag-turn into vapor ang water. That's the temperature affects the evaporation.
Third factor that affects evaporation is humidity. Humidity is the amount of water vapor present in the air. The air around us cannot hold more than a definite amount of water vapor at a given temperature. If the amount of water in the air is already high, the rate of evaporation decreases. For example, the higher the relative humidity, the wetter or cooler it feels outside. Relative humidity means that the air is totally saturated with water vapor and it cannot hold anymore, creating the possibility of rain. The fourth factor is wind speed. The evaporation rate increases with increasing wind speed. With the increase in wind speed, the particles of water vapor move away with the wind, decreasing the amount of water vapor in the surrounding. With wind moving over a water or land surface, it can carry away water particles, which leads to an increase in the amount of water vapor in the atmosphere.
Physics of evaporation. Evaporation is the process by which molecules in a liquid spontaneously become gaseous and escape the liquid state. Evaporites are the resultant mineral precipitates accumulating in and around an increasingly saline residual brine that has reached a state of supersaturation with respect to a particular mineral salt or salts. Water molecules in the liquid phase are in continuous motion and so will collide. As they collide, they transfer energy to each other in varying degrees based on how they collide. Evaporation, then, is a simple matter of solution kinetics in this milieu of molecular motion, and it responds to varying degrees of heat absorption at the molecular scale. The key factor determining how fast the liquid could evaporate was not the temperature difference between the surface and the liquid, but rather the difference in pressure between the liquid surface and the ambient vapor. For example, evaporation of liquid into the air is strongly affected by the insulating properties of the air itself. So for these experiments, the process was observed in a chamber with only the liquid and vapor present, isolated from the surrounding air, then to probe the effects right at the boundary between the liquid and the vapor. The researchers used a very thin membrane riddled with small pores to confine the water, heat it up, and measure its temperature.
The physics of evaporation process is based on the process of providing sufficient energy for breaking the bonds between water molecules. The fact of supplying the system with heat causes water molecules to become more increasingly movable, which results in increase in distance between them. The higher the temperature is, the more water molecules escape the surface into the lower layers of the air. Liquid water transforms into gaseous state. This physical cause for this phenomenon is called the Brownian. Brownian movement is the erratic random movement of a microscopic particles in a fluid as a result of continuous bombardment from molecules of the surrounding. Examples: movement of dust motes in a room, diffusion of pollutants in the air, diffusion of calcium through bolts, movements of hole of electrical charge in a semiconductor.
So now we will tackle about the measurements of different factors for evaporation. There are three main methods for direct micrometeorological measurement: the eddy fluctuation method, aerodynamic profile method, and the Bowen ratio method. The eddy fluctuation method, it measures the water vapor above a surface in conjunction with the vertical wind speed and temperature profiles. These have to be measured at extremely short timescales to account for eddies in vertical wind motion. In aerodynamic profile method, it is based on a detailed knowledge of the energy balance over a surface. The fundamental idea is that by calculating the amount of energy available for evaporation, the actual evaporation rate can be determined. The measurements required are changes in temperature and humidity giving vertical humidity gradients. In Bowen ratio method, it is similar to the aerodynamic profile method but does not assume as much about the atmospheric conditions. The Bowen ratio is the ratio of sensible heat to latent heat and requires detailed measurement of net radiation, soil heat flux, temperature and humidity gradient above the surface. There are two techniques in indirect measurement: the evaporation pans and the lysimeters. In evaporation pans, it is the most common method for measurement of evaporation. A large pan of water and a water depth measuring instruments or weighing device underneath that allows you to record how much water is lost through evaporation over a time period. In lysimeters, it is a vessel or container placed below the ground surface and filled with soil, on which vegetation can be cultivated. It is a multi-purpose instrument for the study of several phases for the hydrological cycle under the natural conditions. One major difference from evaporation pan is that a lysimeter allows percolation through the bottom, although the amount is measured. Percolation is necessary so that the lysimeter mimics as closely as possible the soil surrounding it. There are methods or procedures for estimating evaporation from open water: the pan evaporation, the mass balance, energy budget, bulk or mass transfer, combination equations, the equilibrium temperature method, and the empirical factors. First is the pan evaporation. The use of pans of water for measuring evaporation dates back to the 18th century. It is done in visible way. However, despite numerous studies, it is very difficult to use data from pans except in specific circumstances. Honam, in 1973, carried out a review of methods for estimating lake evaporation from measurements of pan evaporation, and much of the following is drawn from this source. Next is the mass balance. Evaporation is calculated as the change in volume of water stored and the difference between inflow and outflow, where E is the evaporation rate from the water body. P is the mean rate of precipitation over the sampling period. Q sub Ri is the surface inflow rate. Q sub Ro is the surface outflow rate. Q sub Gi is the groundwater and seepage inflow rate. Q sub Go is the groundwater and seepage outflow rate. And V is the water stored, and S is the surface area. For the energy budget, evaporation from a water body is estimated as the energy component required to close the energy budget when all the remaining components of the budget of the water body are known. Example is the residual. The energy associated with evaporation comprises two components: the heat required to convert liquid water into water vapor, or the latent heat of vaporization, and the energy of water vapor molecules carried from, or the advected carried from the water body. The bulk or mass transfer. A simple derivation of the bulk transfer equation is given by Sin during 1991. It has the form where C is the mass transfer coefficient, U is the wind speed, and E sub S and E are the saturated vapor pressure of the air at the water surface temperature, and the water pressure, or the water vapor pressure of the air at the reference height. For the combination equations, for the Penman and Presley-Taylor equations and the Penman-Monteith equation. Next, the equilibrium temperature method. Edinger, during 1968, introduced the concept of an equilibrium temperature and associated time constant, determined from meteorological data, towards which the water temperature is driven by the net heat exchange. From this, he was able to derive an expression for the temperature of a well-mixed body of water as a function of time and water depth. Once the water temperature is estimated, then it can be used to estimate the evaporative and sensible heat fluxes, the heat storage, and the long-wave radiative loss from the water. Next is the empirical factors. In operational estimates of evaporation, empirical factors to convert evaporation rates measured or estimated for one type of land surface, or the reference evaporation, to those of another have been used for some time. They are comparable to the use of pan coefficients to convert measurements of evaporation from evaporation pans to those of other water bodies or land surfaces, and consist of simply multiplying the reference evaporation by an empirical factor. For the midwinter, from November to February, the empirical factor is 1.67. For the spring and autumn, from March to April, September to October, the factor is 1.43. For the midsummer, from May to August, the factor is 1.25. For the humid environment, too light to moderate wind, the factor is 1.1. From humid environment to strong wind, the factor is 1.15. And the dry environment, from dry environment to light to moderate wind, the factor is 1.15 also. From dry environment to strong wind, the factor is 1.2. So that would be the measurements for evaporation.
The methods or procedures for estimating evaporation from open water are the following: pan evaporation, mass balance, energy budget, back or mass transfer combination equations, the equilibrium temperature method, and the empirical factors.
Here's the first method. It's pan evaporation. The use of pans for measuring evaporation dates back to the 18th century. It is done in a visible way. However, despite numerous studies, it is very difficult to use data from pans except in specific circumstances. UNAM 1973 carried out a review of methods for estimating lake evaporation from measurements of pan evaporation, and much of the following is being drawn from this source.
Mass balance. Evaporation is calculated as a change in volume of water stored and the difference between inflow and outflow, where E is the evaporation rate from the water body. P is the mean rate of precipitation over the sampling period. Q sub Ri is the surface inflow rate. Q sub Ro is the surface outflow rate. QGI is the groundwater and seepage inflow rate. QGO is the groundwater and seepage outflow rate. V is the water stored, and A sub S is the surface area.
Next is energy budget. In this method, evaporation from a water body is estimated as the energy component required to close the energy budget when all the remaining components of the budget of the water body are known, meaning it is the residual. The energy associated with evaporation comprises two components: the heat required to convert liquid water into water vapor, and the energy of the water vapor molecules carried from the water body. And here we see the formulas that are being used for this method.
Back or mass transfer, a simple derivation of the back transfer equation, is given by Sini and others. It has the form where C is the mass transfer coefficient, U is the wind speed, and E sub S and E are the saturated vapor pressure of the air at the water surface temperature and the vapor pressure of the air at the reference height.
Next is combination equations. Simply, as time passes, people come up with different formulas in estimating evaporation, but also as time goes by, equations get combined in order to come up with more precise outcomes. In this slide, we see Penman's and Presley-Taylor's equations get combined, and also Penman's and Montate's equations. These formulas are now being used for estimating the evaporation in open water.
The equilibrium temperature method. Edinger et al. Introduced the concept of an equilibrium temperature and associated time constant determined from meteorological data towards which the water temperature is driven by the net heat exchange. From this, he was able to derive an expression for the temperature of a well-mixed body of water as a function of time and water depth. Once the water temperature is estimated, then it can be used to estimate the evaporative and sensible heat fluxes, the heat storage, and the long-wave radiative loss from the water.
The last one is empirical factors. In operational estimates of evaporation, empirical factors to convert evaporation rates measured or estimated for one type of land surface, which is the reference evaporation, to those of another have been used for some time. They are comparable to the use of band coefficients to convert measurements of evaporation from evaporation pans to those of other water bodies or land surfaces, and consist of simply multiplying the reference evaporation by an empirical factor. In here, we see the factor of seasons and the level of humidity and also the strength of wind. That's all for our report about evaporation. Thank you.